So, just out of curiosity, how many people here have worked or used Tableau or is familiar with it? So there's a decent representation. So a couple of comments since you brought up Power BI, and I kind of feel compelled to just say a couple of words. So Tableau does work with SAS. I think that was one of the things you were looking at. And I think all of the other things you talked about, like your checklists, Tableau also meets it. But these days, I think you're going to find a lot of vendors meets those criteria. And what it really boils down to these days is just really evaluating and bringing the product in and trying and seeing what works for you. So, so I will start by saying the talk that I'm going to give today is actually kind of a Cliff Notes version. And normally this is delivered in a 2-hour format with a hands-on workshop. So I will state that if there is an interest in wanting to do the formal hands-on workshop, I'd be happy to come in and do it. And it's also the same type of learning sessions that we actually have at our Tableau customer conference, which is actually coming up in November. So a little bit about me. I've worked for Tableau for 6 years in the pre-sales and technical solutions role. I've worked for other software companies and also management consulting companies. Side notes about me, I'm a foodie. I have a side hustle where I actually teach at a local community college as an adjunct professor, teaching Tableau, and also a boot camp instructor for a data science school here locally. So the intended audience for the presentation and the workshop is some basic knowledge of statistics. And in particular, what I'm going to highlight are the statistical capabilities of Tableau with respect to doing analysis using distribution, descriptive or summary statistics, and modeling. So this is just a quick preview, and I'll touch on all of these different type of ways to work with data. So why visual analysis? How many people here have heard of Anscombe's quartet? So a few. So the premise of this, and this was actually a research that was done in 1973 by Francois Anscombe. And the point made here is you can take 4 data sets, and these are the 4 data sets labeled 1, 2, 3, and 4, and you can do some basic descriptive statistics. And what you will find with these 4 data sets is that they have the same mean for X, the same variance for X, the same mean for Y, and then approximately the same variance for Y as well. There's a little bit of a plus or minus on the error. And then the correlation between X and Y in all cases happens to be identical or nearly identical to 3 decimal places. And their linear regression, basically the formula for that is identical. So you would be led to believe that the data sets are highly correlated, right? Meaning they have the same descriptive statistics. But the reality is, once you actually visualize the data, it tells a different story. So with the first data set, you can see that it seems rather random and scattered. There isn't really as good of a tight fit, if you will, to that particular line. And then when you go to the second one, you will notice that it has more of a kind of a parametric curve to it, right? So that almost suggests, again, that a linear regression really isn't the best way to represent that data. With the third one, you can see that the data shows strongly linear, except for one data point that basically skews the result to give you the same equation, linear regression equation. And then you'll notice with the last one, it's also aligned, but it's actually a constant. And there's one data point that skews it to give you, again, the same behavior. And so the whole point about just relying solely on descriptive statistics, as Francois Anscombe has determined, it requires visual analysis of your data as well to really get some true insights when you're talking about looking for your anomalies, exceptions, and outliers. So we're going to talk about a couple of the ways that Tableau can actually visualize data for statistical analysis. The first one is basically using histograms. So while I don't have the opportunity to demo Tableau, what you will find working with Tableau is that everything about Tableau is drag and drop and point and click. It is truly an easy to use product, and yes, it's been around the block a lot longer than, say, Power BI. I mean, it was basically born out of a Stanford research project back in 2003. And the one thing that I will say that certainly distinguishes the products is actually the core with which Tableau continues to develop its product. It's really centered around a very positive user experience and also a very easy to use interface. It also keeps pace with Power BI, monthly updates, and then major quarterly releases. But again, I think you'll find a lot of the ways with which to do analysis. There are a lot of different choices in menu, either through Show Me or otherwise an Analytics tab that shows you how to do it. So Tableau, in addition to doing basic histograms, can also do cumulative histograms. Tableau can easily do percentiles. For us, this is what we refer to as a quick table calculation. Once you have your data set, you can easily convert over from your raw data set into an analysis from percentiles perspective. You can also represent bands for percentiles if you'd like, so you can determine the percentile groupings, whether it's 25%, 10%, or whatever custom increment you'd like. Tableau also does traditional box plots, and there's a couple of ways that it does this. It has actually what we refer to as a Show Me guide, and it also has an option on the Analytics tab where you can drag the box plot over your data, and then it will represent it. So let's take a look at how Tableau does a box plot. So it starts out with your interquartile range, which is essentially your 50% around the median. It can give you the choice to label your 1.5 times the standard deviation from your interquartile range. You could also set that to minimum or maximum. But again, one thing here that Tableau does well is also identifying your anomalies and your exceptions or your outliers. So you can see once you've basically charted your standard deviation, basically the whiskers at the end, you'll now notice that anything beyond that are probably your exceptions. You can hover over any of those data points and take a look at what that data is. So again, these are your outliers. Tableau also does what we refer to as automatic summary statistics. So on any chart, there's a menu option that right away brings you up everything around the particular metrics or KPIs that you're monitoring, and it'll give you things like your sum, your average, your minimum, your maximum, the median, what the standard deviation is. And then it also does some other things like skewness and excessive kurtosis. In both cases, skewness again is trying to indicate the tendency from which your extreme values might, fall from one side to another. And again, kind of just, do you have a normalized data set, or do you have a data set that has, high outliers? And also, it determines your, essentially the excessive kurtosis. So again, looking for, do you have a tendency to have outlying values that are beyond the normal distribution, or do they fit within a normalized curve? So Tableau can also do modeling statistics, essentially applying mathematical functions to the data in order to surface hidden insights. So it does this by doing unsupervised classifications. Examples of that are trending and regression lines, as well as forecasting and also clustering. So with regards to trending, you have the choice to do linear, exponential, logarithmic, polynomial, or power. So you can try any of those options to figure out which one provides the best fit to the data that you are essentially analyzing. And you can also use it to describe the trend line. So in general, what you're looking for is determining the distance from the curve to the data point and minimizing the square values of these distances. So with any trend model, you can describe it. It can give you a variety of attributes like the R-squared value, the p-value. And then based on that, you can then again determine, do you have a good fit for the data, or do you need to consider a different model for how you're analyzing? Tableau also does forecasting similar to like it does trending. So it uses smoothing, simple exponential smoothing. And so out of the box, if you have enough data points, and here it says the minimum is one measure and then one dimension, and then also a date field or an integer field to be able to do that. It can then do a forecast projecting outward from the historical data. So the things that you can do to influence the forecasting include changing the seasonality, the granularity of the time view of the data, as well as the trending and the exponential smoothing. So forecast models can be additive or multiplicative or seasonal. And you can change those parameters to see which one produces the best results for what you're looking for. So just like with trending, you can do a description of the forecasting, and it will tell you the details about how it determined that. Tableau also, out of the box, can do k-means clustering. So whereas the traditional methods can be rather involved, Tableau, again, it's a drag and drop. You take the data set, you say, I want to do a cluster. It'll give you parameters for choosing what are the attributes you want to cluster by, and how many clusters you want to see, and then it'll do a calculation to determine the number of clusters. So Tableau uses Kolinsky's algorithm to determine K, and also uses Lloyd's algorithm to compute the distance from the center point for each of the 3 clusters to every point in the data. Just like with trending, you can also describe and forecasting, you can also describe the clusters. Additionally, as you group the data, you can actually drag and save the clusters off for future use and analysis. So these things get then, these groupings that are determined by the cluster can be saved off and used to do further analysis and apply these as filters, if you will, to other dashboards or data visualizations you have created. Let's see. So Tableau can also do correlation. A variety of our means for doing and working with functions is in our calculation library. So we can also make callouts to Python or R to do integration. We can also integrate with other products like MATLAB, and also work with SAS datasets. And that's basically the net of my presentation. So again, this is a Cliff Notes version of the workshop that we normally do for about 2 hours, and it covers basically these different types of distribution and modeling techniques with respect to statistics in Tableau.
So now the speaker is Peter Baumgartner from International, and the title is Modern Techniques for Data.
Let's start on the first slide. There we go. Good to go. All right. Perfect. All right. Good afternoon, everyone. My name is Peter Baumgartner. I'm a data scientist at RTI International. I'm here today to talk to you about some modern methods and techniques for exploring text data. So let me start off with everyone's favorite, audience participation. Who has dealt with text data in any capacity before? All right, cool. Those of you that have not are going to do your first analysis today. Little did you know what you were signing up for. Also means that everyone in the other room is totally missing out. So before I get started, just some housekeeping. This talk is pretty high level. It's not very technical. On the last slide, I have a link to my slides and the code used to generate any of the data or visualizations you're going to see here. So if you miss anything, or you're like, wow, this guy talks fast and I have no idea what he's saying, as long as you see the last slide, you'll be saved. There's a link there that'll get you all the information that you need. So let's start out with everyone's favorite, the word cloud. So the word cloud, I would say, is a tool that people use when they have text data and they really don't know what to do with it. So I picked a word cloud on the internet that had an open license so I could put it in my PowerPoint, and I'm not going to sit here and trash talk word clouds. I think they're fine. This is a word cloud of a bunch of tweets from this conference that was held in 2010 called Science Online, and I just want to use it as an example to kind of call out some of the issues I have with word clouds and where we can go from here. So we'll use it as kind of a benchmark. So the first thing I noticed when looking at this is that the largest two words are science and online, and the conference was called Science Online. So I would call that not particularly insightful in terms of an analysis. Another thing I see is if you look kind of above the letter N in science, you'll see blogs, and if you see kind of on the right-hand side below London, you'll see blog. Wouldn't it be great if there was a way that we kind of like combine these words so that they're kind of some sort of root form so that we could standardize and aggregate and understand the text in that way? Another thing I'm seeing is right above the E in science, it looks like there are some URLs. So one of the things I want to know is how is the algorithm that's making this word cloud actually deciding to break apart these words into these tokens? So to kind of summarize my issues with the word cloud, it's a good first start, but it always leaves me just asking a bunch more questions about the data that I have. Some questions like, how is it tokenizing? So how is it breaking the text into those individual words? What tokens might it be excluding? So you'll notice we didn't see words that we would expect to be in there, like the. It's obviously excluding something. That might be something that we want to know what it's excluding. Can I differentiate between nouns, verbs, and adjectives? So it'd be interesting to say, what are the objects that people are talking about? What are the nouns? What are the actions that are being taken? What are the verbs? And how are people describing things as the adjectives? That'd be great if we could pull those out. Can I combine tokens with the same root word in a meaningful way? So that was kind of the blog and blogs idea that I called out there. Can we sort of standardize those? Which tokens are unique for this corpus? So can we compare to like everyday English and see what's specifically unique about tokens included in this collection of text or this corpus versus everyday English? Can I see a token used in context? So I actually want to see the tweets behind each of those words to understand how they're using those words. Words have multiple definitions, and so it'd be good to see an example of how those words are used within a context. How will this scale to larger amounts of text? So if you've got more than 1,000 tweets, what are you going to do with that if you're going to get to 10,000 or 100,000? Or if you have longer documents, like how is a word cloud going to handle that? And finally, can I cluster words by their use? So my goal in this presentation is to hopefully give a process or a method to answer all of these questions through interactive visualization. Now, this is a workflow that I usually take on client projects. I can't show you any client data, so we're going to do our own analysis. It's going to be awesome. I figured we are at the GASP conference, so we're going to talk about statistics. So what I did was I pulled a data set from the website Reddit. So Reddit, if you are unfamiliar with that, it's a kind of a combination of like a link sharing social media site and a discussion forum. And they group the parts of the website into these communities. And I pulled all the posts that people had made and the text from the statistics and Ask Statistics communities for a little over 3 years of data. So this ended up with 30,000 total posts. 60% were from the statistics community and 40% were from the Ask Statistics community. So we're going to do a giant text analysis and just see what people are talking about. This is already, hopefully 30,000 is too much for a word cloud, so we're definitely going to see the need to use some more advanced methodologies here. So the first thing we have to learn is this process of tokenization. And tokenization is the process of taking a string of text and breaking it up into whatever semantic units make sense for your analysis. So typically we use words. It doesn't have to be words. You can do character-based, you can do sentence-based, but typically everything starts with words. And so for this example, you see kind of a visualization of what this looks like here. But tokenization is something that it's important to have control over, because it's a process by which about 80% of the problems that you have in tokenization are solved by just splitting when there's space between words. But then the other 20% are like all weird edge cases that are going to depend on your context and the data that you're going to have. So one example is punctuation, right? So we've split out a question mark here, but if you were just splitting on white space, what happens when you have a word like Mr. or Mrs., right, an abbreviation? Or what do you do with contractions? Or what might you do if there's a hyphen or a dash in the middle of your word? So tokenization is something that you want to have control over. So whenever I'm doing anything with text, I do everything in Python. I use this library called Spacey that you might have heard of in some of the other sessions. And one of the nice things about Spacey, it has a built-in tokenizer that's really fast, but also allows you to plug in other modules and extensions that might do things a little bit different. So for this analysis, I actually used an add-on package called SciSpacey, which is intended for parsing scientific text. I figured if we are dealing with statistics, there might be some formulas or equations or just some things that are a little bit different than dealing with standard English text. So we're going to use a different tokenizer. One of the other things that's nice about Spacey is that after it tokenizes, it gives you all these attributes with the token. So it's not just splitting them apart, it's giving you all this metadata on each of the tokens. So I pulled out one of the tokens here and called out some of the attributes that it's going to give us after it tokenizes. So for the word is, the lemma is B. And so lemma is this idea that I was trying to get at before of a standard root form of a word. And this is really important to look up, especially, I mean, in every language has its irregularities, but English has a ton of weird irregularities. We picked out a great example, right? So the lemma is be. Kind of a more common example, just irregular verbs. So if you look at the verb to go, past tense is went. You need some way to combine those, and the lemma is the way to combine those. So we're going to get this lemma when we tokenize. We're also going to get the part of speech. So it's actually able through a neural network to make a prediction for what part of speech this token is. That's really important. And it's also going to give us the probability of this token occurring in kind of a generic English text. So if we were to put like all of the English words into a hat of all text that's ever been generated, and we were going to pull a token out of the hat, it's actually kind of interesting. Like almost 1% of the time that token would be is. So this is really important to understand, like how rare is this token in just sort of general English text. So we're going to use all this information after we tokenize the text to help build our visualization. So just to give you an idea of what this data looks like, some people understand this a little bit better that way. What we're going to do is we're going to tokenize, and then we're just going to generate some statistics for this corpus. So we've got a giant data set here. Each row is a lemma. We've consolidated there. We've got the part of speech, whether that word is a stop word or not. This is a common list, a list of common words in English. The corpus count, so how many times this occurred within our collection of documents. We're just going to count that up. The corpus probability, so what's the corpus count divided by how many tokens totally existed in our corpus. The English probability, which is just that number from the token attribute for this. And then what we can do with this corpus and English probability is calculate a ratio. So how much more likely is it that this token appears in our text versus kind of a standard English text? And this is going to give us some relative idea of how unique this token is to our corpus. So when we process all of that data from Reddit, from those two communities, 30,000 different posts, we get about 74,000 individual lemmas. So I hope you're not going to make a word cloud out of that. What we're going to do is make a scatter plot with an interactive visualization and a tooltip. So one of the nice things about this process is that once you've got the data in this format, you can take it and put it in whatever tool your CTO has decided to spend money on, whether that's Power BI or Tableau. Or you can use open source software. So what I've done is use Plotly, which is a Python library for building interactive visualization. So downside is you've got to write code. The upside is that it's free. And so we're going to take a look at this visualization now and actually just do some analysis. So let me zoom out here. So here's what this scatter plot looks like overall. It's kind of hard to get this at the exact right size. Let me just explain kind of generally what we're looking at. So on the x-axis is just the frequency of this token within the document. So tokens all the way to the right occur more. If we had a word cloud, those would be the biggest ones. This ratio of our corpus to an English corpus is on the y-axis. So everything above that horizontal line is more likely or more unique to our corpus than any sort of standard English corpus. So to just do like a basic analysis, I think you could make an argument that the most interesting tokens are probably in the upper right corner of this scatter plot. So here's one, the lemma number, which is a noun. It happens 5,435 times in this corpus. We have the probability. And we also see that example there. So the thing in italics at the bottom is just a sentence that contained this token. So we've added that into this interactive tooltip here. We can see how this word is used in context. As I explore this, I did pull this data from the internet, so I hope it's not going to show anything super inappropriate. Another interesting token is datum. So we're talking about data. It would make sense that data is the most frequently occurring token in this corpus about statistics. One of the things we can do is filter down to specific parts of speech here. So this gets at that idea. How do we filter down to the adjectives? So Bayesian is a common adjective when people are talking about statistics. We can go in here and look at some other stuff like Likert, right? If you're doing a rating scale from disagree to strongly agree, that's a Likert or Likert scale. And so we've got a visualization here where actually the positioning actually represents something. It represents this ratio and how frequent it is in the data set. And we can kind of fully understand the context, this is funny, of a token and get an example of that. So I think this is a really powerful way to understand a large amount of text and get a nice interactive visualization of what's in your text to understand what's going on. So I hope I've answered most of those questions except for one at the very end, which was how do we cluster words by use? All right, I got 7 minutes left. So this part I'm going to get really hand wavy. All the technical people are going to get really mad at me because it's just going to seem like dark magic. We're going to do something on our corpus called word embeddings. We're going to generate word embeddings for every word in our corpus. And what a word embedding is going to give us is a location in a vector space such that words that appear in similar contexts are located near each other. So I always think about it this way. It's kind of like an address, like latitude and longitude is just a two-dimensional vector space. So we can think about it this way. Like it's just going to put words that occur in similar contexts. They're going to form a neighborhood, basically. Now, we have a problem in that when we generate word embeddings, it's really hard to capture the complexity of language in only 2 dimensions where we could see it in a scatter plot. So generally when you build word embeddings, you use, like I used 100 for this one. In this visual example, there's 8 columns, so we'd have an 8-dimensional embedding. We need to get this down to 2 dimensions so that we can build a visualization out of this. So to do this, we are going to use a tool called UMAP, which stands for Uniform Manifold Approximation and Projection. And again, I have all this stuff on the last slide and a website, so you'll have all these resources if you missed some of that stuff. And what it's going to do is project any dimensional space down to 2 dimensions, and it's going to retain some really important properties, basically just that both the local and global structure of your data is retained in this 2-dimensional projection. So you might have used a method like principal components analysis to do this before, where you take the first 2 principal components and then just plot those, and you can get like a good idea of the data. The problem with that for data visualization is that principal components focuses on the global structure because it's trying to maximize the variance that it's capturing in each component. And so if you have outliers, you get something really unhealthy, like one point like way over here, and then like a giant blob of points, but it's really compact over here. because that's where the most variance is, right? And so UMAP is really nice because it balances that global structure with the local structure. And so what we can start to see is where these kind of neighborhoods of points occur in our data. And I'll say, like, if you don't take anything else from this presentation, you can use UMAP on any type of data, and it works spectacularly well for understanding kind of in 2 dimensions what the shape of your data is. So it's really helpful. We're using it on word embeddings because they have many dimensions, but you can use it on kind of any type of data of any dimension. And so just to take a look at what this looks like back on our data set, we're just going to add in these 2 columns that are going to have this 2-dimensional projection. So like these numbers, they're meaningless. Like don't pay any attention to the specific numbers. You're just going to have to believe me that the magic will happen when I show you the plot, okay? So what we're going to do is we're going to plot this 2-dimensional projection. We're going to color it by the English or the corpus to English ratio. We're going to only include words with a ratio greater than 1, just so we have words that are unique to our corpus. And we're going to try and understand all of our text through this visualization. And hopefully it's awesome. So since it retains local and global structure, what I like to do with these plots is try and understand the global structure first. So globally, again, don't pay any attention to what the actual numbers on the axes are. They're kind of just meaningless, but do pay attention to the relative position of all of these points. So each one of these points is a word, and if that word occurs, basically for every neighborhood, those words occur in similar contexts. So when I look at the global structure, like I see there's this kind of big separation, there's a bunch of stuff on top, and then there's kind of this weird, I don't know, like these outliers on the bottom here. So that's gonna be the first thing that I'm gonna check out there. And I'm just gonna zoom in so that this can, people can see this a little bit better. So what is happening is when it tokenized, when people were posting about specific stuff in these 2 communities, they'll often include their equations or their code in their question. And so like everything down here is like a table or a formula or like this person's R code, right? And so it's just a bunch of tokens that the tokenizer kind of like, it follows the rules and it tokenizes. And then what happens is this is really nice because through the word embedding model, it actually understands that these types of tokens occur in a totally different context than normal words. So we're able to see that and basically understand that this whole cluster of tokens here are things that people are including in equations. So that's kind of interesting. And now I'm just going to go around the plot and take a look at some of these other neighborhoods. I typically just look by density. And remember that we are coloring by our ratio, so the yellow points are like really unique to our corpus. So over here, we've got a bunch of tokens that are everyone's favorite statistical tests. So of course, the Mann-Whitney, got your U test, got your Wilcox test, you got your McNamara test, Shapiro-Wilk, right? Brown-Forsyth, who can forget that one? It's classic. So it's able to detect that all of these tokens occur in similar contexts. And so now we can start to understand these kind of clusters of terms here. We go up here, we've got, of course, our kind of like experimental design people talk about within subjects and ANOVAs and Romanovas and 3-way, 4-way, 5-way, whatever way, N-way, single factor. Let's go up to this cluster. We've got different modeling techniques, so mixed effects, Earth, AICC, Tobit. Has anyone heard of Tobit? Yeah. Oh my God. See, I'm learning a lot too, right? So you basically have a whole like lexicon of statistical knowledge here, which is really cool. I'm just gonna look at some of these other clusters here. 23 seconds left. I have a buzzer beater here. Okay, up here, people talk about all the authors and textbooks that they're reading. So I saw Gelman up here. I know there's a bunch of Bayesian stuff. Alexander, Hasty, right? They've got all the textbooks. Over here is like applications and education. So people talk about PhD and certificate. Is a SAS certificate worth it? Over here, you've got kind of sports statistics and dates and stuff. And I think down here, you've got kind of the probability problems and kind of like betting and stuff. So it picked all the Pokemon, of course. You've got all that stuff down here. So anyway, word embeddings, projecting them down to 2 dimensions is a really good way to kind of understand these clusters and tokens within your data. It's really powerful. And I'm not going to forget, don't worry. Okay, so my URL, since I already went to it though, is not white. All right, you are experiencing live PowerPoint here. Let's do this, Notepad. There we go. Make it larger, blow it up. All right, well, I can't make it any larger. If you go to this URL or take a picture of this QR code, it's just modern-text-exploration.netlify.com. I've got links to all the slides there. I've got all the code, so you can recreate any of this, plug in your own data, make that work. I just try something else. Remove hyperlink. Aha. Okay, we figured it out. We got it. Live PowerPoint, live analysis. We're doing it live. You can check all that out. You can play with these visualizations in there. So again, I pulled this data from the internet. I tried to remove anything that was like super nasty. Hopefully statisticians aren't too crude with each other, but not responsible if you find any potty words in there. And then I've also got resources, all the libraries I use to generate this, some other stuff that's helpful. And that's all I got. Thank you.
Okay. You have the advantage of working with English here.
Yes.
It's an analytic language and very easy to tokenize. Have you done anything like this with more difficult language? Right? You might think difficult, I think of Hungarian and unpointed Hebrew.
Yeah, so I have not, and I know to me that's one of the most exciting areas in natural language processing is seeing how people are applying these techniques to other languages. There is a bias towards English in a lot of these natural language processing models. Emily Bender is a researcher who focuses a lot on that. I'd recommend her work. But I have not personally done anything on languages other than English. But I also know now too, like some of the other models that you can use for this sort of stuff. So like for the embeddings, there's some multilingual models that you can use for embeddings that you could basically just chuck in any text and get those embeddings out of there. But I just personally haven't done anything outside